I am DeeDee Lavinder. I'm a software engineer on the Vault squad here at Spreedly. And today I want to take a look at encoding. This is a topic with lots of history where a little understanding can go a long way. The idea from this talk came from a bug that we had here at Spreedly. How many of you have seen examples that could be included here? As I dug in, and don't worry, the bug is fixed, I discovered some interesting things about encoding and its history that I would like to share. Let's start by defining the word encode. To encode something simply means to convert it into a coded form. The purpose of encoding is to transform data so that it can be properly and safely consumed by a different type of stream. Morse code, for example, uses dots and dashes of sound or light, along with varying length pauses to communicate certain characters over long distances. Another example of encoding that we're all familiar with is Braille, where physical raised bumps represent letters and numbers. The goal is not to keep information secret, but rather to ensure that it's able to be properly consumed. In the world of software engineering or computing, encoding is not the same as encryption. These terms are sometimes mistakenly used interchangeably. While they both transform data into another format, encoding uses publicly available schemes that are intended to be reversed. Decoding only requires knowing which scheme was used to encode. You can think of it like a map or a legend or even a table. Encryption, on the other hand, is meant to protect valuable or sensitive information, and decryption is more complicated. Data is transformed using a mathematical algorithm or a series of algorithms plus a secret key, and the intention is that it not be easily reversed. We know computers use binary code comprised of the digits 0 and 1 to store data. To communicate with computers, we have to understand the basics of binary code. The smallest unit of data is called a bit. That's a 1 or a 0. Groups of 8 bits are called bytes, and here are 4 bytes. This numerical system, this beautiful system, maps to all other systems, all other number systems. The way you get from binary to our familiar decimal or base 10 numerical system, number system, is super fun and involves powers of 2. That might need to be a different talk, but here's a quick look at the number systems all lined up. And if you didn't get the joke earlier, now's your chance to figure it out. So using a number system translation, encoding schemes allow us to communicate or share data with computers. It translates those 1s and 0s into language we understand and can process. It's basically a set of mappings between the bytes in the computer and the character set of a language. In the beginning, there were no shared standards for this, and there are certain to be many unremembered encoding schemes from those early days of computing. Eventually, intercompatibility became more important, and in 1960, what we now know as the American National Standards Institute began working on the American Standard Code for Information Interchange, commonly known as ASCII. First published in 1963, ASCII uses 7 bytes to encode 128 specified characters. 2 to the 7th is 128. Remember, powers of 2? So fun. Okay, 95 of the encoded characters here are printable. This includes the digits 0 to 9, uppercase and lowercase letters A to Z, and punctuation symbols. The original ASCII specification also included 33 non-printing control codes. Those are now mostly obsolete. There were other encoding schemes at the time, notably the extended binary coded decimal interchange code used by IBM. But ASCII allowed for the ordering and sorting of lists alphabetically and eventually became the more widespread choice in America. So this is an example of ASCII encoding. Each byte represents 1 letter or character. Now, remember how I said ASCII only used 7 bits? And there are 8 bits in a byte? Well, that left an extra bit unassigned in each byte used. So if that 8th bit were put to use, it would allow for another 128 bytes to be assigned to different characters. So people started making up for what was missing from those original 95 characters. Letters from other languages with accents or different shapes, the pi sign, etc. And there are apparently hundreds of different ways programmers used those extra ASCII slots for characters they needed. Meanwhile, ISO 8859 was attempting to provide encoding schemes for languages other than English. In fact, encodings for all the languages were being developed: Russian, Hindi, Arabic, Korean, and all the other languages in active use on this planet, not to mention the ones not in use anymore. Imagine trying to write a mixed language document. It became clear that 1 byte per character would not be sufficient. Chinese and Japanese both contain tens of thousands of characters. So, multi-byte encodings were created. Here's an example of a 2-byte encoding with 16 bits. This is a very small section of GB 18030, an encoding which covers traditional and simplified Chinese characters. Using 16 bits, or 2 bytes, it's possible to encode 65,536 distinct values. Now we're talking. Except that it's yet another specialized encoding format among many. Look at this list of encodings. Things were getting confusing, and there were major compatibility issues. Then in the late 80s, the concept of a new character encoding system that could handle any character on any computer emerged. Unicode was invented. It added a layer of abstraction to the process by assigning a code point to every conceivable character. It's a ginormous table of over 1 million code points that can be used to represent all the other character sets: Middle Eastern, Far Eastern, Southern, Northern, Western, European, prehistorian, and future characters we haven't invented or discovered yet. Using Unicode, you can write a document containing virtually any language using any character you can type into a computer, including Klingon and, of course, emojis. As of March 2019, the most recent version of Unicode, 12.0, contains a repertoire of 137,993 characters. So I am sure that you are all on the edge of your seats wondering how many bits Unicode uses to encode all those characters. 0, because Unicode does not specify how the numbers are stored in a file. You can think of the Unicode code points as an association with characters. Sometimes a character will even have more than one code point. In our thinking, it's important to keep separate the data represented by the Unicode code point and the encoding, those code points represented by a sequence of bytes. There are several encodings for Unicode, and they exist under an umbrella called the Unicode Transformation Format, or UTF. 3 of the most popular UTF encodings are UTF-32, UTF-16, and UTF-8. They can all encode any Unicode code point or character. The difference is in how much space or how many bits they take to do it. UTF-32 uses 4 bytes for every code point. UTF-16 uses between 2 and 4 bytes, and UTF-8 uses between 1 and 4 bytes per character. You probably already know which is the favorite encoding, UTF-8. I know this graph is dated, but what I can tell you is that the trajectory hasn't changed. Since 2009, UTF-8 has been the dominant encoding of any kind, not just Unicode encodings. In 2019, UTF-8 encoding accounts for 93.3% of all web pages. The percentage is higher for the top 1,000 web pages. UTF-8 is backwards compatible with ASCII, which means that it just works in many situations. So today's takeaway, please use UTF-8. Here's a great resource for learning more, easy to remember. And also, there is no such thing as plain text. Don't let them fool you. Specify which encodings you accept from your users. Correctly parsing a file, any file, requires knowing what encoding was used in its creation. If you guess incorrectly, it could lead to permanent data loss. Also keep in mind that characters are abstract entities, and they can technically be anything. If you were hoping to hear about Base 64, there's lots to say. Come and find me afterwards. Thank you so much.